Hey, I just want to quickly thank everybody for coming. Thanks for the speakers, also for volunteering to give a talk. We have awesome lineup today. Five talks total. Just like one note, we'll start. We'll probably end with talks around 5 p.m., 5:30. Please stick around later. We'll have some beer and more food brought in, so we can meet each other. And if you see people with RocksDB t-shirts, it's probably people on RocksDB team, so you can also ask them any questions you might have about RocksDB. And yeah, I don't want to hold on too much. This is Anthony. He's been working with RocksDB team for past year and working on building transactions. So he'll be presenting his work.
Thanks a lot, Igor. Hopefully everyone's doing okay today. Mic's not on? Just not loud enough. So how am I in back? Can you hear me okay? What does a little bit mean? I could be louder. Can you turn me up a little bit? Or I could just talk louder. How about now? Perfect? Cool. So I'm Anthony on RocksDB team here at Facebook. I'm not sure, some of you probably heard, we're currently working on using RocksDB as a storage engine for MySQL, replacing our use of InnoDB, the more popular storage engine. So I want to give an overview of some of the work that went into supporting SQL transactions using RocksDB. So first, we're going to talk about why we actually want to use RocksDB for our production database, and then I'm going to go into how exactly we use transactions on RocksDB. So why do we need another storage engine? So most people in the room are probably familiar. Flash is getting cheaper, but it's still relatively expensive, especially compared to hard drives. Flash is great at doing reads. It can handle many read IOPS, but it still has limited space and limited write endurance. It's limited number of writes you can do to the total device. And for our workloads, we're finding that we're really bottlenecked on the amount of total flash space we have and the amount of total writes we can do to the device. So it'd be great if we could actually reduce the amount of space we're using and reduce the amount of writes we're doing. So how can we do that? So usually we talk about the problem of write amplification and space amplification. What we mean by amplification is sometimes when you want to write a couple bytes, it turns out that you actually end up writing much, much more to your device. And similarly with space, sometimes when you want to store, only 100 bytes, it turns out that you're actually taking up much more space when you actually hit storage. So write amplification and space amplification aren't great. They cause some problems. And I'm guessing you know where I'm going with this slide. Kaboom. So talk about in our existing databases using InnoDB, we have a lot of write amplification, in particular because even if you want to just write a single byte, a lot of times you end up having to write an entire page to disk. So this causes more writes than you intended. Also, we're doing random writes in a B tree. If you want to write 3 different rows, they can end up going to 3 different pages. And it's possible, depending on how your writes are getting batched up, that you still have to write 3 whole pages. Similarly, B tree blocks can be fragmented, even though in this example it has enough space for 4 rows. It's possible your blocks aren't full. You're wasting some space here. So this is another source of space amplification. And due to this fragmentation, compression is not optimal. If you have 16 KB of data, say it compresses down to 5 KB, you don't actually use 5 KB, you might have to round up to the next nearest page size and end up using 8 KB and wasting some space. So this extra amount of space amplification and write amplification causes a lot of extra writes and a lot of extra space used. So we're wondering, can we reduce this and then not need to use as much flash storage? So let's look at a very brief comparison of LSM tree advantages over B trees. So LSM, log structured merge trees, I'm guessing everyone in the room already familiar with that term. Since they're log structured, the writes are sequential. So it's a less write amplification that we've noticed in practice compared to our B trees. Still, there's compaction going on, and there's still some extra write amplification, but we've been able to tune things so that in practice we're seeing less write amplification compared to our B tree-based InnoDB database. Also, because we're log structured and appending everything to the same log, we have a lot less fragmentation. So this results in less space used and fewer writes. And similarly, because we have less fragmentation, we're also able to compress better, and we're also able to compress larger chunks of data, yielding better compression. So again, here's less space used and fewer writes. So in theory, we should be able to save space and writes. And in practice, we actually took a look about loading our data and looking at it in our existing InnoDB MySQL instance and in our new RocksDB MySQL instance. And if you look at the light blue graph on the left, showing a comparison of space used, and when we load the same data into RocksDB, it uses just under half the amount of space, which is great, because this means we could now fit twice the number of database instances on the same host that we could have. Say it again, we can fit twice the number of database instances compared to the number of InnoDB instances we can fit on a given host. So the graph on the right shows, so if we do put twice the number of RocksDB instances compared to 1x the number of InnoDB instances, even though we're doing 2x the work, we're still doing slightly less writes. So this is great. We can cut our amount of Flash servers down by half. We have a ton of expensive Flash servers, so that's a huge savings for us. Okay, so it's all rosy so far. What are the downsides? So there is a read penalty on LSM trees, read amplification, if you will. So if you're doing, let's say, a range scan on the B tree on the left, once you find the leaf block you're interested in, you can just keep reading all leaf blocks on that level to find all the rows you're interested in. With an LSM tree, you don't just read one level, you may have to read all levels, because the data you're interested in could be spread out across all levels. So in practice, RocksDB has Bloom filters and some caching that helps us out there. So we found that on our workloads, we're doing only about a 50% increase in reads. But as I mentioned earlier, Flash devices are really good at handling reads, and this extra reads are fine because we're saving so much space and writes. And even though we're able to reduce the amount of Flash we have by half, we can easily handle these reads. And we found that the latency is actually comparable. Okay, so how do we actually support transactions in RocksDB? So RocksDB already has some features that help you deal with concurrency. There's atomic batched writes, where you could write 50 keys and guarantee they either all succeed or none of them succeed. We have snapshot reads, where you can take a snapshot in a point in time and then read the state of a database at exactly that point in time. And we have merge operators that actually allow users to build complicated application logic. You can then store your own interesting data structures inside a key and then figure out how to modify them intelligently and concurrently. So this is pretty powerful constructs. However, it's a lot easier if you have a begin, commit, rollback style transaction API, particularly if you have more complicated application logic. Or in our case, we have arbitrary SQL transactions with many SQL statements that application developers are writing all over Facebook. We need to translate those down into RocksDB operations. So the only way to easily do that is to have a begin, commit, rollback style API. So just quickly going over the API, it's pretty simple, as you'd expect, leaving out a lot of the details, but you open a transaction DB similar to how you open a regular DB. You can then begin a transaction and get a transaction handle back. And as you can do puts, deletes, and merge on a DB, you could do put, delete, and merge in a transaction. Won't be visible to anyone else except yourself. You can read from this transaction to see the state of both uncommitted data in your transaction and data that's currently in the DB. And then you could choose either commit this data or roll it back. So we actually decided to implement two kinds of concurrency control, optimistic and pessimistic. I kind of half-assed it on looking for stock photographs that don't have stock photograph written in them. It's supposed to be a glass half empty and a glass half full. Not sure if that came out there. But optimistic transactions are optimistic in the sense that they assume there's not going to be any conflicts as we're executing our writes in our transactions, and we wait until commit time to actually do write conflict checking. So this means commit can fail if we detect write conflicts. These are pretty lightweight. There's less overhead, but they're best for workloads where there's not a lot of contention, where you don't have multiple transactions all modifying the same keys, or good for workloads where you have a lot of writes, but very few of those writes need to actually be transactions. However, if you do have a lot of contention, this is not the best solution, as it's possible if two transactions are competing for the same keys, it's more likely that no one can win. And also, a lot of people don't like the model where write conflicts cause commit to fail. A lot of people would rather know ahead of time if their write operations are going to fail, not having to wait till commit time. So when we're actually building MySQL on top of RocksDB, we're using the second kind of transactions, pessimistic concurrency control. So here, we resolve write conflicts by taking locks. We built a lock manager inside RocksDB. And we know that commit should not fail due to any transactional write conflicts. Commit should not fail because of something some other transaction is doing. The only reason commit could fail, just for the same reason any DB write could fail, if your instance goes down or you run out of disk space. So it's kind of a bit of an oversimplification when I say we avoid write conflicts by simply taking locks. We actually have to do a little bit more work. A lot of times we not only want to take a lock, but we also want to say, has this key been modified since the transaction started? Oops. So since RocksDB is essentially a giant log of write operations, we're able to just use the mem tables to look at what keys have been written recently. So when we attempt to lock a row, we can check, hey, has anyone else written this key, since this transaction started? The advantages of the mem tables are really easy to check. They're in memory. We've added some options to tune the amount of mem table history you have, so you guarantee you have a certain length of history to check. Of course, that means if you have a really long transaction that age is longer than the amount of history you have in your mem tables, then checking the mem tables is not sufficient, and you could get an error saying that the transaction could not detect if there are write conflicts. But we're working on fixing that by enabling us actually checking the LSM tree itself for write conflicts. And there should be some tuning required here to make sure you have enough mem table history that you usually only go to mem tables to actually do your write conflict checking. Okay, a lot of times we're talking about transactions. People want to know what DB isolation level we're supporting. Not familiar with DB isolation levels, just bear with me for a second. But to answer that question, we're actually supporting read committed and a repeatable read when we actually implement MySQL on top of RocksDB. But RocksDB's API is pretty flexible, that we allow the application writer to use it in any way they want to get any particular isolation they want. However, we cannot right now support fully serializable transactions because there's one case we're not yet supporting, and that's I'm calling phantom write detection. Just give an example. So suppose I want to lock all the rows, all the keys between 10 and 40. I look and I see there are 4 keys here. I lock all of them. I think I have all the keys locked. Someone comes in and inserts a 25, and unbeknownst to me, I no longer have all the keys locked. For this reason, we can't get fully serializable transactions. In order to actually support this case, people do things like called either gap locking, prefix locking, or next key locking. In a lot of B tree databases, this is really easy to implement because you already have a B tree that has all your data sorted. You already have a good place to add a little flag on key 20 that says no one's allowed to insert anything after 20. In an LSM tree, there's no, we don't have all our keys sorted. There's no easy place to add this information. We probably have to build a new data structure, a new concurrent data structure to handle this. And in practice, for our giant production workload, this case wasn't really a problem for us. So we decided not to handle it right now. Maybe in the future, we could look into supporting this. So I mentioned the user is able to build whatever isolation level they want. They can do that using a function we have called set snapshot. Before I define what this is, let me give a quick example. So here's a simple read, modify, write. We read a key from the database, we update its value, and then we try and write it back. Say we're reading the value 10, and we're trying to increment it by 1 and write back 11. So read, modify, write is dangerous. If someone else is trying to execute the same code in parallel, two people are trying to increment 10 to 11, it's possible, two people are trying to increment 10, it's possible you won't end up with 12, it's possible you'll just end up with 11 and lose an increment. So this generally isn't safe to do. So how can we actually make this safe? Well, one way, instead of doing a get, we support doing a get for update, which is similar to a SQL select for update. The get for update not only fetches the data, but it also locks it so that we know when we read and the value is 10, we know no one else can be modifying this data. It's safe to increment it to 11 and write it back. So this is safe. And for this simple example, it's a pretty good solution. However, in the general case, the problem we have here is it can be a pain if we require users ahead of time to do a get for update for all keys that they might change anytime in their transaction. It's really hard to reorder your application logic to do this. And when we're supporting arbitrary transactions, we can't just figure out what the transaction is going to lock and lock it ahead of time. So instead, we have a function called set snapshot. And what set snapshot will do is it'll guarantee that after you call set snapshot, any write operation that you do will guarantee that if it's successful, that means we're not only able to take a lock, but we also guarantee that this key has not changed since the last time set snapshot was called. So we read the value, we get a 10, and then we attempt to put 11. We know the put will only be successful if we can tell that no one's modified the same key since set snapshot was called. And in order to support, different isolation levels, the user is free to keep calling, set snapshot to move their write conflict boundary checking as they see fit. Running short on time, we're supporting a couple other features. We're supporting partially rolling back transactions. We don't have to roll back everything. You could just roll back to a save point you set. It makes it easier when we're executing many statements in a transaction. We want to fail one statement, but not the others. We decided not to implement deadlock detection because in practice we found deadlock detection is pretty heavyweight and slow, and we've always preferred to just use timeouts even when we have the option of deadlock detection. Timeouts are easy enough to implement. Also, we're supporting a custom locking API where instead of using RocksDB's internal mutexes and condition variables, you can pass your own condition variables and mutexes. This was useful when we're adding RocksDB as a storage engine for MySQL to use MySQL's concurrency structures. So then you can use MySQL's infrastructure and management tools to end a transaction that's waiting on a mutex. Future work, as I mentioned, we're improving write conflict detection so we can support more longer running transactions. Right now, we're limited transactions must be able to fit in memory. If you have really massive transactions, it's not currently supported. And we're thinking about implementing a simple two-phase commit, prepare and commit model so that a layer on top could actually do cross-instance transactions using RocksDB Transactions. And I think we're out of time for questions, but Igor, are we doing questions or are we just rolling through? Any questions? Oh, set snapshot? So all set snapshot does is it registers a snapshot in the database, similar to how the database already supports a get snapshot method. And then what we actually do is when we take the lock, we lock in our lock table, we then just check the mem table to see if there are any recent changes. Any other questions? Yeah. Mm-hmm. Yes. Yeah, so, oh yeah, sure. So someone mentioned earlier, I mentioned we're not supporting, yes, we're not supporting phantom write detection. So what happens if we have a transaction that's trying to lock all the rows and we found out it wasn't able to lock all the rows because a new one appeared? So this is a question of basically what isolation level you're allowing. So in most databases, you can actually set your isolation level. Right now, currently in MySQL, you could say, do you want, read committed? Do you want, repeatable read? Do you want serializable? And you need to know that if you set your isolation level to read committed, this kind of anomaly can happen. And basically, we're saying that your only options are to set read committed, repeatable read. You cannot actually set serializable, so you need to know this important distinction. And it gets a little confusing because the definition of repeatable read is different in ANSI SQL standards than it is across many different databases. According to ANSI SQL standards, we don't need to support this case, but a lot of other databases do support this case in repeatable read. So it's an important distinction we put in place. And if we get enough feedback from people that this is important for their use cases, maybe we could work on implementing this. Yeah, it's essentially a checkpoint. So basically, halfway through your transaction, you could just set a save point, and you can keep going, and you can decide if you get a conflict that you don't want to roll back the entire transaction. You only want to roll back up until the save point. This is useful if we're executing multiple SQL statements. Let's say executing 10 SQL statements, they each modify 10 rows, and on the ninth right of the last SQL statement, if that statement fails, we're going to tell the user, sorry, that SQL statement fails, but we're going to leave the other statements they executed still in this transaction and leave it up to the user to decide, do you want to keep going or do you want to abort the whole transaction? Oh, sure. The question was, what are save points used for? Yeah, the API to create save points is, I think, just set save point and then roll back to save point. You could, set as many save points as you want and then roll back as many times as you have save points set. The question in front? No, right now uncommitted data does not make it to disk, and that's the reason why we don't support massive transactions. Your transaction currently has to fit in memory. Although if we implement, a two-phase commit in the future, this is something that we could look into changing. But right now, we don't support massive transactions. Any other questions? Yes. Sorry. Can you nest? So you can call it multiple times, and if you are using rollback to save point and save points, if you roll back, it will roll back to the appropriate snapshot. So that's future work. So the plan would be if you support two-phase commit on an individual instance, you would still need a layer above RocksDB to figure out some details about managing which transactions are successful. Sorry, the question was, how would two-phase commit work? So if we had two-phase commit in each instance, you would be able to prepare both instances. And once you realize that the transactions are good to go, they're prepared and ready to commit, then you could write your own transaction identifier to your own persistent log and then commit each one. Yes. Sorry, can you say that again? Oh, that's a very interesting question. I know we have done some perf comparisons, but I'm not sure if anyone's actually done those yet. But we're definitely it's definitely going to be done as we continue to roll this out. And I think we're out of time for questions. So I'll hand it off to the next speaker.